And here you go. So you should see my screen and you should be able to hear me properly. This session is going to be recorded and you will receive an email since you're registered to this webinar with a link to the recording in the next couple of days. Okay, so welcome to this webinar on high-dimensional data analysis, unsupervised analysis. I'm Andrea Valle, I'm product manager for FCS Express. Today online with me, Jeff Tracker, senior applications scientist for OMIQ, and also Greg Veltri from the FCS Express team. It's also here with us. So we're super happy to be with you with this in this hour. So a very brief introduction on what we're going to see today. The agenda, it's split in two. We will see a couple of examples of pre-processing, and you see scaling and downsampling, basically because those are the most wanted. You will probably run them, I will say, like almost every time you do high-dimensional data analysis. And then we will see two examples of actual algorithms, namely UMAP and FlowSOM. So to make this joint webinar a little bit more dynamic, we decided to use FCS Express in the first part and OMIQ in the second part. So I will take care of the pre-processing. Jeff will take care of clustering and dimension reduction. But I really want to be clear, so you can run this entire process, so scaling, downsampling, FlowSOM, and high-dimensional data analysis in general, in both platforms. So you can run this in FCS Express, you can run this in OMIQ. So it doesn't matter whether you have one or the other one. So what me and Jeff would like to do today, together with you, it's going through some of like real data example and play a little bit with the parameters and the variables that are involved in each of those steps. Again, feel free to find your way to the question section of the GoToMeeting webinar dialog. Feel free to type the question that you want. At the end, we will reply, we will answer to your question live. So generally speaking, high-dimensional data analysis, it's performed through a workflow like this. Okay, so you have raw data, like FCS file, let's say. You run some pre-processing, then you run the actual, let's say, analysis with like algorithms like dimensionality reduction and clustering, and you do at the end some like manual gating or like creating some nice picture, high resolution, or like summary statistic and so on. So pre-processing aims to prepare the data for the actual analysis. If you screw up with pre-processing, well, you know the rules, garbage in, garbage out. So pre-processing is as important as the actual analysis part. Like, so how can you perform this entire workflow in FCS Express or in OMIQ? Well, this is the idea. In FCS Express, you can use what we call pipeline. In OMIQ, you can use what we call workflow. But basically, it's the same. It's a way to tell your software which steps you want to run and in which order. So you see, those are two basically identical pipeline, workflow, whatever you want to call them. You see, at the beginning, you have scaling, then you have gating, then you have spade, and then you have t-SNE. So it's just an example. Those are just very, very short pipeline or workflow, as you prefer, and you can run them in both software. Now, again, I want to underline that it's not only a matter of which steps you include in your workflow, it's also a matter of the order in which you add them to your workflow, because these pipelines will be run from the top to the bottom. So if, for example, you move the gate step downstream spade and t-SNE, it means that spade and t-SNE will not be able to access that information. Okay, and the same is the same in FCS Express and in OMIQ. So again, in my first part, we will use FCS Express. We will go through scaling and downsampling, not actually gate downsampling. We will see something a little bit cooler. And then with Jeff, you will go through dimensionality reduction, UMAP, and clustering FlowSOM. Now, why we scale the data? And again, this applies to both FCS Express and OMIQ, and in general, when you want to run a dimensional data analysis in flow cytometry, mass cytometry, spectral cytometry. So the reason is that if you do not scale the data will look like this. and I'm speaking about fluorescences. I'm not speaking about like for a scatter or side scatter, but fluorescences will look like this. So the negative events will be all compressed, and then you have a broad peak for the positive events. And this is because it's something intrinsic in the technique. So the variance, okay, you might say the variability, increase with the increasing intensity. So that's why peaks are broader if you don't apply any scale in the higher range of value. And for us, human beings, this is an issue because we much prefer looking at the data this way, okay? You see, this is the same data that you see on the left, but here at the right, a scale is applied, okay? We prefer this because the two peaks are more comparable, okay? The negative and the positive. Basically, what we're doing is shrinking the point-to-point distance, okay, for higher value, so the distances are more comparable, variance are more comparable, okay? Because the issue is really about distances. So if you look on the left, if you look on the left, you can see that distances are, let's say, of less importance in the higher range, okay? Those two data point B and C, okay, we as a scientist, we know that they come from the same peak, okay? So we know that they are more similar together, each other, sorry, than cell A. But still it looks here that they are much farther than cell A and B, okay? This is 20,000 in whatever unit of measurement you want, and this is like 10,000. So since algorithms like Disney, FlowSOM, and UMAP rely on distances, we need to add them. We need to transform the data with the scaling in a way that distances have at the end the same importance. So after the scaling, the idea is that a distance of 1, okay, in the positive range has the same importance than a distance of 1 in the negative, in the lower range, sorry. Okay, so this is the reason why we scale. I would say almost all the algorithms benefit from the scaling. I can think at one exception right now, which is like FlowAI. FlowAI, it's a data cleaning algorithm. Today we will not see data cleaning, but this is another very important pre-processing step. FlowAI, I mean, the author of FlowAI suggested to run FlowAI on non-scaled, so on these type of data. Okay, but otherwise, for example, today we will see UMAP and FlowSOM. They really benefit from a scaling step. And what I want to do now is to do some scaling in FCS Express and actually show you that it doesn't really matter which scale you want to use. It's really more about the final results. Okay, so here I have a very simple layout, a few gates. Your gating hierarchy might be completely different, but anyway, let's say that we want to focus on this population. I call it lymphocytes, and we want to run some high-dimensional data analysis. So in FCS Express, once you have this gating hierarchy, you go here in the ribbon bar under tools, you see we have transformations. Okay, so this is the transformation dialog. This is where you can access the pipeline tool. Remember, in FCS Express, we call it pipeline, the way of running this type of analysis. In OMIQ, we call it workflow, but the idea is the same. So this is the initial of the pipeline. We can call it root step or like step 0, let's say. And here you have a list of parameters. My suggestion is to keep all of them checked, so that this means that you can access all those parameters in every step of the pipeline. Then in every step, you can select which one you want to use in that step and which one you don't, but at least select all of them here so that they will all be accessible. And now I'm going to add steps, okay, through this drop-down menu. I want to start with a gating step. And in this gating step, I will go straight, I will select lymphocyte. Okay, so this means that the very first step of my pipeline will do a gating and will narrow down the overall data set to the lymphocyte gate. Okay, lymphocyte is just an example. In this case, I want to deal with lymphocyte. And then I want to add the scaling step. So I'm going here, mathematical, and scaling. Okay, don't confuse it with like 0-1 scaling. This is something completely different. This is scaling. Now, which parameter do we want to scale? Okay, we know we need to scale, but which parameter we want to scale? Well, we are scaling because of UMAP. We are scaling because of FlowSOM. So it depends on which parameter you want to include in downstream algorithms. Now, to do something like very quick, I will select all fluorescences. Okay, but you might reason on this. You might say, okay, some channel is empty, so I will not scale it, and I will not use it in UMAP. Okay, so you can think about this and apply to your experiment. Now I will uncheck the automatic here, and I really want to expose you to the option we have here. So for example, FCS Express allows you to use those scales: linear, B exponential, hyperlog, blah blah blah, arcsine H, and I want to the linear one, and I already know, and you know now, that linear, it's not a good scale for fluorescency. So I want to show you why it's not good. So I will apply this pipeline here. Now in this plot, after applying the pipeline, I can access, you see here, the scaled version of each parameter. So let's start with like CD3, okay, for a scatter here. So it's nonsense. Okay, all the data are stacked together. Okay, this is why it's not a good scale. Everything is compressed. Let's try with, I don't know, CD4. Okay, you see how compressed is the negative as compared to the positive. This is not what we want. So just to show you, we can, for example, use arcsine H. Here you have a cofactor. Cofactor is basically the transition point. 5, it's usually the starting point. You want to deal with mass cytometry data. It's not really good for flow data. You can change it, and I want to show you what happened. Like if I increase it, the negative, which is now split by 2, you have this mirror artifact, will start to be more compressed. So this is what we want, like 50, okay, 500, okay, maybe like 2000, okay. So you see, we're making the negative and the positive more comparable. Now, how can you do this? Like instead of opening one plot for each parameter, you can go here, multi-plot. You can create multiple histogram. I just want to show you how it works. Okay, I will create multiple histogram showing the scale data. Okay, you see here? So you can check, and the right scaling, it's when you see the 2 peaks, okay, quite comparable. Okay, you don't see one super compressed and the other one super broad. Another way to do this, it's by using like 2D plots. This is also an option. It's really up to you. And it's still done through the multi-plot. So you can go here. I will select all by X, all by Y, because I want to keep the forward scatter on the Y, and then I want to switch on the X. So same concept as before. Here we go. Now, you see here, you should see that all parameters are properly scaled. Now, you might find some exception. For example, you see this CD3, the negative, it's a little bit too much compressed, okay? And maybe for the CD4, you have the opposite. The negative, it's not enough shrinked, okay? So it might be hard to find like a unique value for all. And the more parameter you have, the harder it will be. So if I increase to feed the CD14, like, I don't know, 5,000, okay, now the CD14 might be better, but the CD3, it's to compress the negative. Okay, you can see it here as compared to the positive. So what you can do in FCS Express, let's say that we want, well, let's say that 2000 is okay for most of them. And maybe we want to simply increase the cofactor for the CD14. Well, I will not scale the CD14 in this step, okay? I will add another step, a scaling step, that I will only use it for CD14. I can literally call it for CD14. And now I will check the CD14, and I will say, okay, I know I want to use arcsine H, and I want to use, I don't know, like 5,000. Oh, sorry, 50,000, too much. 5,000. And let's see how it looks. Okay, so you see, you can still scale them differently. Another way to do this is by using the exponential. So let me go back here. Let me delete this one. I will still scale CD14 here. And I will switch to B exponential. Why B exponential might be a good choice if you are in this situation. So B exponential still allows you to define a fixed number. And if you want, you can also create a second step for the scaling. But otherwise, you can use this option. Below zero, calculate automatically. So this is something special for the B exponential scale. And in this case, each parameter is scaled with its own transition point, its own below zero parameter. So this is something that allows, that helps you, especially when you have a lot, not just like those few parameters. Maybe you have like 40 and you're going crazy to scale them independently. So this is something to keep in mind. But again, you see, doesn't matter whether you use arcsine H, what doesn't matter whether you use B exponential, you can find the right scale for each parameter for your data. So just a matter of like double checking. It's really something visual that you want to do. Okay, and in this case, you see positive and negative are really well balanced in terms of variance in that parameter. Now, the second time is running, the second pre-processing step that I want to speak about is downsampling. So most of the time, we simply want to downsample to speed up the downstream calculation. So we have like 1 million of events. We want to run Disney. I'm running Disney on a laptop. I'm in battery mode and I want to wait like 1 hour. And I want to downsample to like 100,000 and run it in 5 minutes. Okay, that's fine. You can do it with random sampling. You can do it with interval sampling. The crucial point here is that you really want to do that only because of the speed, okay, to increase the speed. But of course, there is some risk. Like if you downsample from like 1 million to like 50,000, I mean, it's really aggressive. I know you should probably not do that. It's really too much in most of the cases. But it also depends on like the complexity of the data set. But let's say that you really want to downsample a lot. Like, well, rare population might be lost. Okay, imagine to have like just 100 data points out of 1 million. Okay, if you downsample to like 10%, you will end up with like 10 data points in that population, and 10 data point might or might not, and this is the risk, be found by the downstream algorithms. So what I mean with being found, it means that you might, like UMAP or Disney, might not realize that that is a population. Okay, 10 dots can be whatever. Okay, well, if you're 100, well, you're simply increasing the chances to found that population. Okay, to map that population in UMAP, in Disney, in FlowSOM, and so on. So another good point of downsampling is that you can use it to actually enrich rare population. This is something that, for example, you can do with the so-called density-dependent downsampling. Okay, in FCS Express we have two. One is called target, one is called weighted. The target, for those of you who remember Spade, okay, was one of the probably most famous algorithm, like 10 years old. And the target density was the density downsample used by Spade. Okay. The weighted density, it's a little bit simpler. So I want to show you. You can play with both actually, just to practice. But I want to show you how it works in FCS Express with a real example. But anyway, those two aims to skew the frequency of population, and most of the time you want to skew it towards the rare population. So you're dealing with the rare population, you want to increase the chance to map them in like UMAP or TSD. So you run the downsampling in a way that those rare population will be preferentially sampled. Okay, so if the original frequency was like 0.1%, maybe at the end of the downsampling, it's like 1%, okay, or 0.5, like 5 times higher. So we can actually look at this one now that I see it. So you see here we have a, let's see how it's rare. Okay, it's not super rare, but sorry, it's not super rare, but anyway, it's like 0.50, okay, without downsampling. Now, let me pause my pipeline. Let me add from the downsampling category the weighted density downsampling. Now, before clicking on run, I want to show you a little bit here. So density dependent downsample calculates the density of events. So basically, for every data point, they calculate the number of data points in their neighborhood. So for every data point, you're basically asking how many data points I have in my neighborhood. And you can guess, like you can easily understand that if you have a lot of data points around, okay, let's say that you are a data point, you have a lot of neighbors, you are in a dense region, okay, and probably that's not a rare population. You're not part of a rare population. If you have very few neighbors around you, you're probably a very rare data point. Okay, you have few neighbors around you, so you are in a sparse region, you're probably a rare population. So this is why this type of downsampling must calculate the density, okay, to basically classify data points in dense and data points in sparse region. Now, the weighted downsampling allows you to define a data size, like let's say 100,000. I should have like about 300,000 overall here. And the weight is the parameter that allows you to enrich abundant, which is usually what you don't care about, or enrich rare population. Okay, if you want to increase rare population, just set it to a negative value. Okay, this can go -10, +10. So 0 means basically do not enrich. Okay, do nothing, like just almost random sampling. So now I will automatically run to just a trick here. So you have two methods, like the exact, which is really precise, or the kernel, which is an approximation. I will use the kernel only because we're playing, but if you have time, feel free to go with the exact method. Anyway, so let me run it. Okay, so I'm not enriching. It's like 0.54 instead of 0.50, right? Now let's try -2, like a slightly enrichment. 0.80, -5. Sorry, 1 minus 1.20. Okay, this is 2.5 -8. This is really aggressive. Okay, almost 3 times. Okay, of course, this is let's say it's the frequency after the downsampling. Okay, it's not the real frequency in the raw data. But this means that you're increasing the chance to map this population. Okay, last thing that I want to show you in the last few minutes from this first part, it's what I'm doing now. It's downsampling 100,000 events overall. So this is actually a merged data. Sorry, merged data. Okay, I have 3 data files here. Okay, so you know when you want to run high dimensional analysis, you concatenate the data. You can actually concatenate the data. You can do it in like virtual concatenation, but anyway, you need to put them together. Now, if you run this downsampling, actually any downsampling, like random sampling, but as a step like this, it means 100,000 events overall. What about if you want to actually sample the same number of events from each file? Well, you can do this in FCS Express by adding this step. It's called classification folder. Whatever you put in this folder, any step will be run independently, okay, on the classification that you select. In this case, we only have one classification, which is the file identifier. So if I put the weighted density downsampling inside this folder, this step will try to sample 100,000 events from each file. So let's do it. And here we go. So what happens, for example, if you do not have enough events from a file? Well, this is exactly the situation. Let me show you the number of events. So file, this is 100,000 events. This is 100,000 events. And file number 3 was really small. You see, we don't have enough events, so we'll basically keep all of them, ideally. If I lower it down to like 10,000, let's see. Okay, now we're quite close to have the same number of events. Now, you might still see some discrepancy because remember, we are trying to balance like a fixed number of events, in this case 10,000, and a fixed number of like enrichment, like -8, which is a little bit aggressive in this case. If we relax a little bit one of those two parameters, for we lower it down to like -5. It's a little bit less aggressive enrichment. Now we really have the same number of events. Okay, but anyway, you can do this with the classification folder. So long story short, we saw how to find the right scaling. And again, doesn't matter which scale you apply. Okay, B exponential has some advantage like the automatic below zero detection, but otherwise you can achieve a good scaling with arcsine H as well. So no problem. And then we saw downsampling. Okay, different downsampling exists, like interval sampling, random sampling, target density, weighted density. It's really a matter of which is the final goal, okay? Whether it's just speeding up the downstream calculation, or whether it's just like enriching in rare population. So let me go back to the presentation, and I want to conclude this first part by telling you that if you go on the website, in this case, the FCS Express website, denovosoftware.com videos, you can find a lot of videos about high dimensional data analysis. We have 19. So feel free to poke around. We have also like educational video. And I think these are really useful especially if you're getting started. So next part, Jeff Tracker will take care of giving you tips on UMAP and FlowSOM. And in this case, we will use OMIQ. So let me make Jeff the presenter. Here we go. Jeff, you should be able now to share your screen. Let me know if this is not the case.
All right, I think it is. Can you see mine?
Yes.
Perfect.
Stage is yours.
Thank you so much. Yeah, so all right, everyone, we get to step into the second half of this presentation now. We'll talk about UMAP and FlowSOM. And again, just as a refresher, you can, well, I'll be using OMIQ for just a few of these examples, but you can also do UMAP and FlowSOM, obviously in FCS Express, and you can do scaling and downsampling in OMIQ. So let's see, let's take off. So first things first, Andrea had already mentioned this, but it's very important to make sure that you're using well-cleaned, well-scaled data before you start using these algorithms. That's because these algorithms are essentially another step into an analysis, but it's a step abstracted away from the actual single cell data as it's been acquired. So it can be harder to realize if there are compensation errors, unmixing errors, scaling errors, if there's still population artifacts like debris, dead cells, doublets, antibody aggregates. Those are all harder to detect after you're looking at the results of these algorithms. So I want to emphasize really quickly to make sure that you're putting clean data into these algorithms. We're going to be talking today about UMAP and FlowSOM. UMAP is a dimensionality reduction algorithm. It's one of the more common ones. Another very common dimensionality reduction algorithm is TSNE, and there's many versions, especially if you've been in the field for a little bit. I'm sure you've heard about them. The one I recommend if you're just getting started in this space, if you're interested in trying these things out, is OPT-SNE, OPT-SNE. Because it's a little bit simpler to set up. But we're going to be focusing on UMAP today, and then FlowSOM. So we'll talk a little bit about what these algorithms are, and then the good places to start in high dimension analysis tagline for this presentation is basically we'll be talking about the specific settings and what they do, or some of the things that have the most impact on these algorithms and what they do, and how you can learn to change these settings to get a better result. One of the common misconceptions I see when it comes to things like this is that if the algorithm works the first time when you start it, then the results are good. The computer generated them, so they must be okay. And a lot of the time, if it works, that's great, but you can make a better representation of your data by tuning some of these parameters. And so that's what we're going to be taking a look at as we step through this. So what is UMAP? UMAP is a nonlinear dimensionality reduction algorithm. And what that means is the distance between these islands is less meaningful than just if an event is in the same island or is in a separate island. So principal component analysis, PCA, is a linear dimensionality reduction algorithm. And without going too far into the deep weeds of what goes on under the hood, the distances in PCA are meaningful, and you can compare things, actually XY distances on those. With UMAP and with TSNE, they're both nonlinear. So the important takeaway here is just if you have two events in the same island, that means they're essentially the same or very similar cell type. If they're in different islands, that means they're a different cell type. But just because two islands are closer to each other or further away from each other, that doesn't mean that they're more evolutionarily related or separate or anything. It just needs to have some space to put these. So essentially, after you run these algorithms on your data, if you use phenotyping channels in the setup of these algorithms, then you will end up with each island containing a different subset of your cells. And so this happens to be a UMAP figure from OMIQ 69, which is a 40 color phenotyping panel. Basically, if you want to check it out, it's a very thorough approach to developing a 40 color spectral panel. I helped contribute to the analysis, so this data set is kind of near and dear to my heart. But this is healthy human PBMCs, and all of these islands are different cell subsets in that PBMC space. Another kind of attribute, I guess you'd call this, of UMAP is that it's designed to focus more on global structure than on local structure. And what I mean by that is UMAP's goal is to give you a clean visualization or representation of your events, and to separate the different cell subsets basically as far apart as they can get. But it sacrifices a little bit some separation inside of these subsets. So for instance, this is the CD4 island right here. And these little clusters, these little subsections here are the CD45 RA positive and negative, but CD25 positive, 127 low kind of Treg. These are the Treg-like cells in here. And you'll notice they're just on one side of this island. They're not separated entirely. That's because they're only different from a lot of the other cell subsets in this particular panel just by their expression of CD25 and CD127. So they're not different enough in UMAP to break out into their own little islands. Whereas in this case, this is basophils, for instance. They're very different from all the rest of the cells here, and so they end up in their own little space. And so, oops, we'll take a step forward in just one second. But the global structure is basically focusing on separating your cell subsets from each other, and is not quite as good at showing you heterogeneity inside of these cell subsets or these islands. TSNE is a little bit better at showing you differences inside of your cell subsets. So just if you're trying to make a decision about which one to use, that's kind of what's going on here. But regardless, in dimensionality reduction, the goal is to take the sum essentially look at the differences in many, many dimensions and distill those differences down into just 2 dimensions to make it easier to see essentially all the different phenotypes you have, what's in your tube, and then you can either gate on this or you can do clustering and display it on this, and we'll see that in just a little bit. But the goal is to help you, number one, look at the different phenotypes that you have or the different functional subsets if you use functional markers in your dimensionality reduction. And then also you can use TSNE or UMAP to QA or QC your data. So if you go and you see lots of these little islands in between your large islands, that might mean that you haven't gated out all your dead cells, or there's some debris still, or there's antibody aggregates. Or if you're running a longitudinal study, you can overlay your different batches with different solid colors in your UMAP or TSNE, and you can see if you have batch effects. It will be then kind of on you to figure out what's causing those batch effects, but you can kind of diagnose that with help from these dimensionality reduction algorithms. So they're very useful. I run them on almost every experiment that I end up helping analyze. So I would recommend trying it out yourself if you haven't yet. I'm not gonna step through all of these. This is recorded, and so if you are watching this as recording, feel free to pause here if you want a more focused step-by-step definition for each of these settings. But on all of these algorithms we're going to be talking about today, UMAP and FlowSOM, there is a place where you can select which files that you want to be part of the analysis. There's a place for you to select which channels you want to be part of this particular calculation. And then there's a place for these settings. And we'll take a look at this in the software in a little bit. But essentially, there's two main ones that we're going to be covering today because they have the most effect on the outcome or on the result. So one is neighbors here. And this is basically inside of both UMAP and TSNE, there's a setting that you can use to kind of help it either focus even more on the global structure or tell it to focus a little bit more on the local structure. So, different cell types inside of the CD4 island, or global is, B cells compared to monocytes, or NKs versus T cells, or things like that. So neighbors controls that, and we'll see an example here. And also minimum distance. So minimum distance is essentially a very responsive parameter. It changes the structure of your result a lot, and it controls kind of how much white space is between your islands, or how tightly the events are allowed to kind of group around the middle of their island. And so these can have, these two parameters can have a very large effect on the outcome of a UMAP. So I'm going to switch really quickly here into the software so you can kind of see what this looks like. And you'll see here, this is a little bit more complicated workflow than what Andrea had pulled up earlier. But essentially, I've done my compensation or my spillover correction. I've done my scaling. And then I've done some gating, I've done some subsampling. Then I'm free to add in, an algorithm task. And in this case, if I'm going to add in a dimensionality reduction task, I have a lot to choose from, and we're going to select UMAP. And so here we have a place to select all the files we're interested in. We can select all of the parameters we're interested in. In this case, not the linearly scaled scatter or time parameters. We've already covered that earlier. Thanks, Andrea. But instead, just the fluorescent phenotyping markers. And then here we have the settings panel where we can choose kind of which settings we're looking at. And again, the default settings for neighbors is 15, and this is the one that controls, basically what part of the structure we want to emphasize, global versus local. And then there's minimum distance, and this controls, again, how grouped or squished around the center of the island each of our events are. So we'll switch back here just so you can kind of see what this looks like. Oh, and we had it, we already had it pulled up there. So this is what a UMAP looks like with those settings from this data set, from this 40 color spectral data set looking at healthy human PBMCs. So this is just another rerun. It's just a quick example, and we're coloring by CD4 expression. So you can see there's this CD4 island. It's kind of well separated from the other islands. It's off by itself. This one is kind of dim. It turns out that this island is the monocytes, and they have that kind of very dim but still not zero CD4 expression often. And these might be maybe the CD4, CD8 dual positives, So there's, a few little intermediate populations, but this is the four, this is where that CD4 population sits with the default settings. So the defaults are intended to be a pretty good start. But if you change these, let's see what those look like. So if we lower the neighbor number here to 3, so that means focus much more on the local structure. You get the CD4 is much more spread out, but actually at the cost of this being kind of a valid projection. You couldn't draw a gate in between the CD4 positives and the CD4 negatives anymore. So 3 is definitely too low. And if you see an outcome like this on your particular UMAP, think about raising the neighbor number a little bit to kind of help it more cleanly separate your populations. If you increase the neighbors to 45, you can see it is much, essentially, it's even cleaner and more well separated than that initial step. So if you're going for a really clear separation between your different cell subsets, but you want to sacrifice a little bit of what's going on inside each island. Increasing that neighbor number is something you can try. The next the one I wanted to talk about is minimum distance. So the default is 0.4. If you'd lower that to 0.1, you're allowing the events to squish around the center of each island much more. And so you're encouraging, again, more space in between the islands. In this case, we don't need this much white space between these islands. I don't need this much space to draw a gate around any of these populations, and I'm just losing information now. I'm losing how this population might relate to the rest of these in this island, and so on. And so this would be a little bit too low for me personally. I would probably work on increasing this. If I increased the minimum distance though up to 0.9, which is near the maximum, you can see we start to lose that separation between very different cell populations. So between our CD4 T cells and not, and even our monocytes and these other populations, whatever they are, I can't draw a gate even if I needed to in between these populations. It would be close, but I wouldn't be comfortable putting that in like a figure for a journal article or something. And so this is just something to keep in mind, that if your first result out of UMAP doesn't really look like it's cleanly separated, or it doesn't necessarily, it's kind of a confusing result, feel free to rerun either the UMAP with these different settings or with a different seed. And this is something I want to touch on just really quickly, because sometimes I get this question from people. The seed value, if you use all the other settings the same, you use the exact same files, the exact same channels, but you use a different seed, there's some randomness that's kind of salted or seeded into the process when it goes about separating these populations. And if you use a different seed, it'll make different decisions randomly at those points. And so you'll still get the same events in your CD4 island, but it might be that this CD4 island is on this side of the plot as opposed to this side. And so if you end up with a confusing result and you're like, wait a second, my PI is totally, they're gonna sit down and be like, but what's this? And why is it here? And why is this island so close to that island? Feel free to rerun the seed. You'll get the same populations in the same islands. The islands will very likely, though, be in a different orientation to each other. And again, because UMAP is nonlinear, that's okay. That's not the important part of the information. The important part is what events are inside and what events are in separate islands. Okay. So that's UMAP. And again, if this is brand new to all of you, we have some resources at the end that will be helpful, but also feel free to ask questions in the questions interface in this GoToWebinar, and we'll collect those and then either answer them in line if it's not too complicated, or take some time after the recording finishes to step through those. So don't be shy about asking questions. The next step, or the next algorithm we're going to be talking about is FlowSOM. And I also wanted to take just a second to talk about the difference between clustering and dimensionality reduction, because this is another thing I see sometimes. Some people, when they show either a UMAP or a TSNE, they'll say, oh, well, this cluster is positive for CD4, but this is actually, these aren't technically clusters. This is why I've been calling them islands or groups of cells. It's because UMAP is not a clustering algorithm, and the result that it spits out are not clusters. FlowSOM does that, SPADE is clustering, Phenograph is clustering, PARC is clustering, but not UMAP and OPSNI. And so because it's that time of year, I'm going to use one of my favorite analogies about the difference between these two. For those of you in the US, or if you're familiar, it's almost Halloween, which is where kids go around to the neighborhood and go trick-or-treating and they get candy. As a kid, when I did this, I'd come back from my trick-or-treating and I would take all the candy I got in my little bag or my little pumpkin bucket or whatever, and I'd dump it out on the kitchen table. And dimensionality reduction is like putting the similar candies next to each other on your kitchen table. You put the M&Ms next to the Skittles because they're both small and round. One is more chocolate, the other is more sugar, so they'd be in separate islands, but they'd still be, broadly speaking, kind of close to each other. If you had whole king size candy bars, maybe you visited a really great house, those would be in their own separate island. If you had like the little bit of honey candies, those are the ones nobody liked. Sorry if you like those. They would be in their own separate island. And so you're just sorting out. You don't have to make hard decisions. A clustering algorithm in that particular situation would be like if your parents gave you little plastic baggies. They say, hey, here's 10 little baggies. Now you have to take all your different candy types and make the decision about which of those baggies those candy types have to be in. And so clustering then requires kind of hard decision making about, hey, I've only got 10 baggies to put this piece of candy in. I've only got 10 clusters to put my cell in. Which one does it go in? And so UMAP has a lot more freedom to show rare cell types. Like this particular one right here, this is a very rare but very different event because it's very far away from everything else, and there's not very many of the events right there. So it will certainly just end up in its own island. But if I then had to cluster this data, if I put in 10 or 15 clusters, it's very unlikely that this event or those few events right here would end up in their own cluster because they're just so rare. They'd get lumped in maybe with their nearest neighbor. And that's a little bit of what Andrea was talking about with the density dependent downsampling or the target downsampling. It helps kind of clustering algorithms deal with that a little bit better. But in kind of the vanilla approach, it's very unlikely they would end up in their own cluster. So clustering algorithms essentially have to make the hard choice of what bucket or bin or cluster to put all of your events in. And so FlowSOM is one of them. It's a very commonly used one. There are other ones that I've already mentioned, but FlowSOM is designed just from the ground up to be very, very fast, to handle a lot of events and to be good at clustering while it's doing that. So it's one of the more popular ones in cytometry. A quick aside, actually, I do want to mention this, that these dimensionality reduction and these clustering algorithms, we're using them for cytometry data, but especially things like TSNE and UMAP and PARC and KNN. These are algorithms that are used much more broadly by the total data science community in all of their respective fields. So whether it's satellite imagery or social networking or stock market or anything like that, these are algorithms that many other people are utilizing in their own analysis needs. Self-organizing maps, they come from outside of cytometry. There's a huge basically corpus of experience and information and materials out there about these algorithms. They're not just specialized flow tools. It just so happens that flow data is really well suited to the application of these tools. So it's definitely worth going out and exploring a little bit. And I have some links at the end of the presentation to give you some insight there. But essentially, focusing again on FlowSOM. FlowSOM is a clustering algorithm. In OMIQ, you have the ability to select, again, which files you want it to use. You have the ability to select which channels you want it to use. In this case, again, all these phenotyping markers. And then you have some settings, and I'll go through and explain these settings really quickly. Essentially, it does a two-step process. The first step is that FlowSOM clusters your data into a number of buckets. And what the X dimension and Y dimension is it defines kind of how many buckets or clusters your data gets split into. By default, it's a 10 by 10 grid, so it ends up with 100 clusters. However, you can increase that if you have a more heterogeneous sample or you have a really high parameter or channel count in your panel. It might be better to be 12 by 12 or 15 by 15 or even 20 by 20. That will yield a much larger number of initial clusters. And after it's split all of your cells into that number of clusters, the next step is that it goes and it says, all right, some of these clusters are going to be the same kind of cells. They're going to be pretty similar. And so it combines the similar ones into meta clusters. And that's this step. And that's kind of the more tangible step that a lot of people are interested in. When you get a FlowSOM result, you have you know, maybe 10 or 20 or 40 or 60 different meta clusters, and that's what a lot of people actually practically work with in cytometry after they run FlowSOM. And so the first two here control how big that matrix is. Again, if you're doing a 15 color panel on PBMCs, 100 by 100 is great. If you're doing a 40 color or 45 color panel on bone marrow and they're all phenotyping markers, you might want to use start with a 15 by 15, and that'll help you get your smaller populations of interest in their own cluster. This next option down, this next parameter down, is the number of training iterations. It's totally okay to leave this at 10. It's a pretty robust parameter. It just, I essentially always leave it alone. It doesn't do a lot to the outcome of a particular run. Distance metrics, we don't have a lot of time to really get into the weeds on these, but the important takeaway here is using Euclidean distance metrics is a great fit for cytometry data. There's the ability to use different distance metrics if you're looking at different data types. So some people doing machine learning are comparing pictures of dogs to pictures of cats, or different handwriting samples between people, or different yields from different oil fields or whatever. Those might use a different distance metric, or might be more effective with a different distance metric. Euclidean is basically almost always the one you want to be using for cytometry data. So you can leave that one alone. And then this is the important part. This is the kind of the most important one for FlowSOM, is the number of meta clusters. So elbow meta clustering is the default, and this is essentially you telling FlowSOM, hey, take your best guess at the right number of clusters. However, you also have the ability to say, you know what, also do a meta clustering version with 10 meta clusters or 40 or 60, and you can type in any number of comma separated values here, and it will redo the analysis using each of these values as the number of meta clusters. And as long as the number of meta clusters is lower than the number of initial clusters you started with, that will work. You can even put 1 here if you wanted to. Sometimes we tell people to do that as a setup for cytonorm if they don't want to split their cells apart by different populations. If you've tried to use cytonorm before, that will make sense. If you haven't, check out our support material, and we have a little section in there about that. But essentially, this is the number of meta clusters that will get spit out at the end. And this is not a solved problem. Phenograph doesn't require you to input a hard number here, but there's still a neighbor number that you can change. But SPADE and FlowSOM and many other clustering algorithms from across the board still require you to put in kind of the desired number of meta clusters. And so my guidance here is basically have a smallest population of interest in mind. So say you're very interested in studying Tregs, and change that number of meta clusters until you get your Tregs in their own meta cluster, or maybe your CD45 negative Tregs, or essentially whatever small population that you want to measure or describe or investigate. Have that to be in 1 or 2 or 3 meta clusters, and that's a good place to start. It's not necessarily always the answer, and if you're doing discovery work, like for instance, hey, I want to look at 50 lupus patients, and I don't know what my smallest population of interest is. That's a conundrum. That's part of science, right? In that case, I'd recommend just skewing a little bit high. So skew high on clusters, like maybe 250, 300, 400 clusters, and a little bit higher on meta clusters. So 50, 60, 80, 100, something like that. And then look for interesting changes between your experimental groups or things like that. But there's not a single correct answer for meta clusters. It's up to you to understand the biology. So what I'm going to talk about here is why I actually don't recommend having FlowSOM guess. The elbow meta clustering, the default option there, basically all it does is it looks at the y-axis here is heterogeneity, and the x-axis is number of clusters. And so if every single one of your events was in a single cluster, that cluster would be very heterogeneous, very large variety of events in that cluster. And that's not good, obviously. But if you had 140 clusters, it's basically the same result as any of its neighbors, 139 or 141. You're not helping split apart your populations anymore. And so what FlowSOM does is it looks for the elbow in this graph and selects that as the quote unquote right number. But it doesn't understand any of the biology. It doesn't know what events in your sample, what you're looking at. It doesn't know how your panel is constructed or what channels are more important or less important to you. It's just taking kind of this totally unbiased, but therefore maybe a little ineffective view of your data and just trying to balance the heterogeneity to the number of clusters. And so I would really make sure to go back and characterize, if you do use the elbow metaclustering method, go back and make sure you know what the clusters are and that you can find your smallest population of interest. And in the last few slides, I want to talk about how people do that so that you're not just sitting there stranded thinking, great, he told me to check what my clusters are, and I don't know how to do that. This is looking at some manual gates overlaid on a UMAP. You can also take your clusters and overlay them on a UMAP as well. And if you have questions about any of these things, like mechanistically, for OMIQ, I'd recommend going to our tutorial because we cover it in our walkthrough. But there are certainly resources for FCS Express as well in theirs. There's not enough time to really get into every tiny tweak, but I just want to make sure that you know it's possible. So instead of doing manual populations overlaid on the FlowSOM, you can overlay FlowSOM clusters on the UMAP. This is how I like to look at the result. As you increase the number of clusters, you can see it does a better job at splitting apart these populations into more specific subsets. So in this case, we're looking at 60 different clusters on the same data set. And you can tell there's a lot of heterogeneity, but some, like this pink island that happens to be naive CD4s, there's just a lot of naive CD4s and they all look the same. So they don't end up kind of breaking apart into smaller clusters that easily. Whereas some of these other islands end up just being, like confetti or sprinkles. There's all kinds of different little subsets in there. So one way that people often look at clusters is by making heat maps of every channel versus every cluster. Sometimes this can be good, although it can be difficult to know which of these clusters are more abundant than others. And if there's any kind of non-unimodal distribution here, that's tough. And so essentially, you can look at this this way. This is more qualitative, overlaying your clusters on UMAP, but then coloring your UMAP by expression levels. This gives you a little bit more of a better idea of what's going on in each cluster. But again, it's a little qualitative. And so this is what I'd recommend, at least in OMIQ, that you can do, is there's a special x-axis option when you're building these plots. And you can overlay your cluster onto total. And you get an idea of the distribution of the events in every channel. You get an idea of the abundance of that particular cluster. And then you can tile this or permute this for every cluster. So you can get a really nice overview of all of the different clusters, what their frequency is, and then what their expression levels in each of the channels are. So with that, just to wrap up really quickly, we have a tutorial at this link for how to do all these things in OMIQ, and we have a quick FAQ about the website or setting up an account and everything like that. I mentioned that all of these tools have lots of information out there on the internet as well. They all are open source, and so they all have GitHub pages, and they all have the journal articles that were used to debut them. So this is one in particular for UMAP, but whatever algorithm you're using, there will be resources online for it. Towards Data Science is a great blog that covers a ton of different facets of the whole data science community. Obviously not very often in Flow, but just broadly speaking, it's a great way to get exposed to kind of the things happening in the field. And then to make these colors, this is just one of my little pet favorite tools. It's not affiliated with us at all, but I used it to make this figure. And so it's a great way to kind of color your different clusters if you're overlaying them on a UMAP. And so if you want to try out either of these software packages, you can do that for FCS Express at this link or at OMIQ in that link. And if you have any questions or you need a little more insight, or you just are sitting here thinking, wow, that was a lot of information and I'd like a little more clarity, that's okay. It's okay to feel that way. Always feel free to reach out to us, either support@denovosoftware.com or support@omiq.ai, and we're happy to help. So thank you very much for taking the time to hang out with us for a little bit and learn about some practical steps you can take to tackle high parameter analysis. We're happy to stick around for a little bit extra for some questions, but I think with that, we'll end the recording.